as a reminder, a perpendicular bisector is a segment that intersects another segment at a right angle and at its midpoint. Equidistant equal distances from 2 points. Good Lord, yeah, that's really terrible. Perpendicular bisectors have the following properties. This theorem is actually a biconditional, but I'm going to write each condition separate from each other. Perpendicular bisector theorem says that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. As I mentioned just a second ago, the converse is also true. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Let's do some quick finding of some values here. How about we find the value in the first one? Find the value of x in this diagram. Well, let's see. Point D is on a segment that is intersecting AC at a right angle and at the midpoint. Therefore, D is on the perpendicular bisector of this segment. So what do you know about the distance of D to each of these two endpoints, Greg?
They are equal to each other.
They are equal to each other, so we could write an equation to relate the two sides together. What would that be? What'd you end up with? Yeah, so when you're done with this equation, when you're done with setting up this equation where the two sides have to be equal to each other, you end up with blah blah blah, x is 1. Is point C on this perpendicular bisector of segment AB?
Yes.
Why? Kelsey?
Because of the converse of the perpendicular bisector.
Because of the converse of the perpendicular bisector theorem. How about we just say that yes, it is equidistant to both A and B, which means that the converse of the perpendicular bisector theorem is true. All right, let's take it up a notch here. Perpendicular bisectors are neat, but there's some more things to go. They're actually way more neat if we put them in context of triangles. Let's add a sub-definition to one of your vocab words, concurrent.
Not concurrent.
In terms of mathematics, they're both basically the same thing. Your vocab definition and how we're going to use it in mathematics. Your vocab definition was what? Two things that happen at the same time, right? Concurrent events. Concurrent concurrent objects in geometry are two objects in geometry are concurrent if they share a point, or more specifically, three or more objects that intersect at the same point. So, we said two things that happen at the same time are concurrent events. Concurrent things in geometry are objects that intersect at the same point. They're concurrent there. The point where they intersect is called the point of concurrency. Or point of concurrency. The circumcenter of a triangle is our first quote-unquote center of a triangle. We're going to see, I think, by the time we're done with this chapter, we'll have, I believe, 4 different points that we could call or label the center of a triangle. This is the first one. The circumcenter is the point of concurrency of the perpendicular bisectors of a triangle. Point of concurrency, meaning the point where the 3 perpendicular bisectors intersect. Of the circumcenter being on the 3 perpendicular bisectors is the following. The circumcenter is equidistant from all 3 vertices of the triangle. The circumcenter is the same distance from all 3 vertices of your triangle. No matter how you draw the triangle, no matter what's going on, the circumcenter is always the same distance from the 3 vertices. So let's see, a consequence of this would be, say, if I tell you that G is the circumcenter of this triangle, let's find the length of G to A. What's the length of G to A?
25.
25, why?
So that's the length of GC.
Because that's the length of GC, and it's also the same length as GB. They both have to be, all 3 have to be 25. Absolutely. Well, if these are the perpendicular bisectors, you can actually do some more with this. We can actually find some more missing parts. Like, what's this length?
20.
20. It's a perpendicular bisector, then it cuts this side in half. Therefore, this is 15. This is 24. This side's got to be 25. You could do some other calculations too, like you could use Pythagorean theorem to find these lengths. Well, if you wanted. Good. Okay. Well, the last example here is example 2. Where should this company put a distribution center? Now, I know that there's a star in the middle here, but what would be a better name for the place to put the distribution center so that you know it's equidistant from the 3 restaurants? These 3 guys are restaurants. Where would be the best place to put it? If it could find the circumcenter of this triangle, then it would be the same distance from all 3 restaurants. Would be ideal.